Have you ever wondered how computations can be compared so efficiently? In this video, we'll be explaining state commitments and how PRT applies this to efficiently map and compare computation proofs. We'll be using this mathematical operation as a simplified example to illustrate the process of generating and comparing state commitments. The process starts with dividing the large computation request into smaller steps, which are then handled one after the other. Our sample request is divided into 3 smaller steps. The first step is executed by validators, then their storage updated, after which a Merkle tree is generated from the updated storage slots of the validator. A Merkle tree is a structure used to create state commitment efficiently by recursively hashing pairs of leaf nodes, which are storage slots in this case, until a single node referred to as the root node remains. Step 2 is then executed next, followed by a storage update and a new Merkle tree generated for that step. Finally, step 3 is executed, and like others, storage is updated and a Merkle tree generated from the new state. Using Merkle trees, validators effectively map and prove their state transitions efficiently, and even slight modifications are propagated upwards, leading to visible changes in the root node. At the end of this process, we have the updated storage of the validator as well as the root hash of the storage update at the end of each step. The state hash from each step are then paired once more to generate a Merkle tree whose root is referred to as the computation hash of the request. In the scenario where a dishonest validator max wrongly executes step 3, storing the value 50 instead of the actual output of the execution, this change would generate a different root hash in the Merkle tree for step 3. This new state hash for step 3 will further propagate upwards to generate a different computation hash, which would trigger a dispute in the verification contract. When Bob the honest validator and Max the dishonest validator both submit different computation hash for the request, the verifier creates a match between Bob and Max. This match is a recursive binary search over the hashes for each step to identify the first step where both validators submit different hashes. The bisection starts at step 2, and when the verifier confirms both validators submitted the same hash for that step, it then moves further to step 3, where it identifies the first bisection. On identification of this step, the verifier executes this single step, then obtains the expected hash for that step, which it used to identify and disqualify Max as a dishonest validator, then proceeds to accept Bob's claim as valid. Although this example paints an understandable scenario, real computations would be much more complex, and when broken into steps would run into millions or even billions of steps, thereby requiring the use of sparsely generated state hashes and multi-level tournaments as explained in our previous video.